me what it is.
dy of t over dt.
dy dt.
Plus 3y of t equals delta t, and then a semicolon, y of 0 equals 0.
All right. Y of t equals 0 equals 0. Now, this is something where now you're going to see how Laplace transforms make differential equations simple. Right? This is the bottom line. When we take a look at this, we're going to take a Laplace transform of both sides of this equation. This is something you've seen before. Everybody's been exposed to this that's sitting here. We take a Laplace transform of this, we get s y of s minus y for t equals 0 plus or 0 minus, they're the same, right? Then take the Laplace transform of this, we get plus 3y of s. Do y'all follow me on this, what I'm doing, class? How many do, everybody here? Just taking Laplace, you see what? Just Laplace transforms of each term. And what does this equal? Well, that equals delta t. Well, the Laplace transform of delta t is just 1, isn't it, class? I started you off with the simplest possible one. Now, when you take a look at this, the next thing we do, yeah?
No.
It's just a Laplace transform. You take the Laplace transform of the equation, not just one function now, the entire equation, right? Now we come to here, and I gave you the easy one. There's no initial condition, so that goes away, right? So now I factor out y of s, and I have y of s, and here it's going to be, really it's 3 plus s is equal to 1, correct, class? This is the simplest possible thing. And that's why Laplace transforms are so powerful. They solve differential equations in a trivial manner. I mean, they're algebraic instead of really doing integral differential equations with integrating factors and all that stuff. So that means y of s, if you look at this, y of s is just equal to 1 over s plus 3, correct? Now that is y of t. It's the solution to the differential equation in the s domain. What function reveals this transform? And this is where you have to know your transform pairs. I know that e to the minus at u of t renders 1 over s plus a. Correct, class? Now the scale on this thing, there's just 1 in front of it, right? So the only thing we know is a here would be equal to 3, and that means my y of t is simply equal to e to the minus 3t u of t. Bingo, that's it. That's how simple it is. And that's how come with circuits problems especially, this is a gift. Because you write any differential equation, right? Just write it in terms and then throw it into a Laplace transform thing, group the terms that are defined just in terms of s, and then the function y of s, or the solution you're looking for, x of s, and then do an inverse Laplace. We're going to be talking more about that too. Any other questions about homework? Yes?
Could we do 3.6c?
Yeah, but tell me
4e.
3.6c. Go ahead.
4e raised to the negative 2 parentheses t minus 3
Go ahead.
times u of t minus 4.
T minus 4? Is that it? And you want the Laplace transform of that. Now, here's what I'm going to tell people about. You always think about fitting forms. What do I know? Well, I know that e to the minus 2t times u of t would render simply 1 over 2 plus s. Do you all agree with that, class? I'm going to go through this and try to make sense of it. Do you agree? Now, when we have this, right? By the way, if you want to, this is one you can easily brute force to, and I'll do that in a second. I mean, I could just stick this as the function x of t into the definition and do the integration, and you'll see it that way. Maybe I should do it first just to show you. Whenever you see a simple exponential that starts at a different time like this, here's how you brute force this. You go to the definition of Laplace transform. X of s is equal to the integral from 0 to infinity of x of t times e to the minus st dt. First, everybody has to know that, like the back of their hand, right? That's something that's automatic. Now, if I stick that function in here, what do I get? I get the integral from 0 to infinity of x of t. Now look, it's 4e to the minus 2t times 4e to the minus 2 times minus 3, or really plus 6, right? So I can take that. I'll write it in here by itself. I'm going to have 4 e to the minus 2t, right, times e to the plus 6. And then I have u of t minus 4 times e to the minus st dt. You all see this? By this time, most of you probably have seen the trick for this. It's not really a trick. Do you all agree that 4 e to the 6 is a constant? Everybody? So I'm going to take it out front. Now, next question is, what does this do to the limits down there? The u of t minus 4. Class? The lower limit starts at 4. Right? Now, what do we have? Well, this, can't I group the exponentials together, class? So this is going to be e to the minus, and it's s plus 2t dt. Do you agree with me, everyone? Does everybody see what I've done? Now, this is of the form of e to the minus at. I want to make sure everybody sees this, because sometimes, especially if you, for me, if I don't have a cup of coffee in the morning and I try to do something, I can miss the obvious. So I'm going to just show you this. Anytime you have the integral of e to the minus at dt from a to b, that's really equal to minus 1 over a, e to the minus at, where t is equal to a, and then t is equal to b. Agreed? One of the things I tell people is change the limits with a minus sign in front. So I just change that, make it plus, make this b, make this a. Lower becomes, the lower limits becomes the upper limit and vice versa. And now, go over here and do the same thing. That's dt right here, right? So what are we going to get? The 4 e to the 6 stays by itself, right? Remember that s plus 2 is a constant. It's a. So then it becomes, divide this by s plus 2 here, right? Now I'm going to take the limits and I'm going to flip. I'm going to have e to the minus, and here it's going to be s plus 2t, where t down, well, I'm going to do it. T becomes infinity here, and, I'm sorry, s. No, t. T becomes infinity here, and t becomes 4 here, right? So that means it's going to be 4 over s plus 2 times e to the 6th, and then it's just going to be times e to the minus 4 times s plus 2 here. And the infinity limit goes to 0 because e to the minus infinity is 0. Follow me, class? And that's the answer. Now, it may not be in the form given in these solutions, but it is nevertheless the answer. One thing you can see here, when I break out the e to the minus 4 times 2, that's e to the minus 8, right? E to the minus 8 times e to the 6th is e to the minus 2, correct? So what I could do to simplify it is this. I can go ahead and get rid of this and get rid of that and just put e to the minus 2 here. And that would be the answer, and that's acceptable. I use the word brute force when I'm actually going to go ahead and do the integration. That's a brute force way. Follow me? Everybody? And that's the simplest way for this in some respects. Now getting back here, what I want to do is properties. Here's the problem I have. I would like this argument to be this argument, right? So how could I make that happen? Well, if I multiply this by e, now if you just think about this, I want 4 there. What I have to do is multiply this by e to, just show you what I'm talking about. What I want to do is get e to the minus 2 times quantity t minus 3 to have t minus 4 there, right? Well, if I put a plus 1 here, or I'm sorry, a minus 1 here in there, then what I'm going to have to do is take e, that would be e to the minus 2 times minus 1 would be e to the 2. E to the minus 2 outside. Do you see what I'm talking about? Now this, therefore, would become e to the minus 4, right? and I took an e to the minus 2 out front. Do you all see what I'm doing? I'm trying to manipulate this thing to fit forms. What form in particular? Well, I know if this is true, and this is my x of t, right? Then I know x of t minus a times u of t minus a does what? It transforms as just e to the minus as times x of s. How many see what I'm doing? This is a standard, do you remember doing this proof right here? This is a standard property you have to know, right? So now let's look at what I'm up to. Well, I want the transform of this, right? If I call this my x of t, right here, I'm calling this my x of t, then what I have, I've modified this, so now this is going to be equal to e to the minus 2 times t minus 4, and it's going to have an e to the minus 2 out in front, right? You all see this, class? The only thing I'm doing is manipulating this to fit this form here, right? I've got the e to the minus 2t down, right? This is just thing. Now, what I have to do is take care of the scale, and I'll do it right here. I see that there's a 4 that's going to appear in a minus e to the minus 2. So I'm going to say my x of t is actually going to be rendered 4 e to the minus 2 times e to the minus 2, t, so that means I've got to put the 4 e to the minus 2 here. You all see what I'm doing? I'm just fitting the form. There's nothing tricky about this. So here, this is a transform that I see. And I see that if I just get rid of that minus 4, cover that and that, and just let it t, right? Now, what happens when I have the minus t, or t minus 4 here? The only thing that happens is this phase constant comes there, and it's e to the minus 4s, right? So this becomes e to the minus 4s, when this becomes t minus 4, and this becomes t minus 4. And that's the transform pair you're looking for. The tip I give everybody on these is when you take a look at this thing, try to forget the time delay initially. Just look beyond that. Without the time delay, I've got a simple exponential, e to the minus 2t times u of t, correct, class? Now that time delay actually needs to be adjusted because it was minus 3 at first. So that's how come I adjusted it with multiplying by minus 2 and then putting e to the 2 times that. Now I've got the exact form I want, and it's easily manipulated. Do you all agree with me? Show of hands here, how many see this? I gotta make sure you guys see it, right? And by the way, you gotta spend a lot of time on this stuff, because these proofs and these transform pairs, you have to know like the back of your hand. You'll be using them in everything, in EMAG and comm theory. You'll use them in random signals and systems. It's gotta become almost second nature to you at a point. All right, so you're gonna see this over and over again. Any question about this? Any other question? I hope I answered. Who answered this? Who answered this? Did you? No, you.
Yes.
You got another one? It's a good time to do them. You must have. No? Anybody? Yes.
3.78 is 25 times the
Let me first.
gas.
Give me a second. One thing about these things, it's almost like make this a challenge to yourself, like you're doing a crossword puzzle or playing chess or something, and these things become kind of interesting. How can I get that? And you're looking at tricks, you're looking at fitting the form and trying to find, I always recommend properties. Try to use the properties before you brute force, unless it's simple like an exponential or a delta function. You can brute force those very easily, but other than that, properties are where it's at. What's the problem?
It is 25 times the cosine of 4 pi t plus 30 degrees times delta t.
And they want the transform of this?
Yeah.
This is a no-brainer. This is one, the minute you see a delta function transform is over. You don't need to go through properties. We can go through properties, but the minute I see this, I just go to the fundamental definition. I say, all right, what is it? The Laplace transform of this function, if this is x of t, is simply that function, right? Integrated from 0 to infinity, 25, right, times cosine of 4 pi t plus 30 degrees. times delta t, that's my x of t, and then I multiply it by e to the minus st dt. Now I evaluate that integral. I'm going to stop to make sure this point's really driven home. Remember, you see a delta function in any function, I'd go right at the integral. Yeah, we can do properties and get there, but it's so much easier to take one look at that and ask the question, what does the delta function really do in here? It sifts the value of anything it's multiplying at the point the delta function goes to infinity or turns on, right? So when does this delta function turn on? Zero. So I evaluate everything next to it at 0. What is e to the minus 0? 1, right? That goes away. What happens here? I'm left with just 25 times cosine of 4 pi t, which is 0, plus 30 degrees. So it's cosine of 30 degrees. And that's it. That's why delta functions are godsends for you. Because if you see them and you're asked for the Laplace transform, it's a no-brainer. Y'all follow me on that? Show of hands here. Y'all see that? Remember, go to the fundamental definition with delta functions, and most of the time with exponentials too. Not all. Exponential multiplying by sine or cosine, something like that, you can. But I do that. Another one. I'm trying to make sure I can go through the problems and tell you how I think about the problem, not how the book does. You got another one for me? Yeah.
I got one, but I forgot it.
By the way, I think on GroupMe, did you post that, Liddy? Somebody posted that very one, I think. Isn't that one on Group?
Yeah, I think,
Yeah.
yes.
Yeah, I thought so. Thank you for doing it. Spend your time interacting on Group. They'll tell you that's the best single thing to do on social media sites is use them for your benefit. Interact, there's no dumb question. You can complain about me, it doesn't matter. I don't care. I hear it all. Anyway, next. Which one? Yeah.
Could you do the circuit one?
Yeah, I wanted to get that one. Because here's now your application to your major. Here it is, right in your home domain, all right, circuits. And you just got out of circuits, right? With Earl. How many had Earl? All right, he's the best, in my opinion. All right, so you have a circuit with a given voltage that I'll put in. Then you have a resistor, isn't that right? Resistor here. Is it capacitor or inductor?
Inductor.
Inductor. And I'm just going to call this R, call this L, right? And what's the function here?
20 e to the minus 3t.
20 e to the minus what?
3t.
3t u of t? And we want to solve this for I of t or what? Voltage across the inductor?
Voltage across the inductor.
Okay, we can do this several ways. We want this voltage, V of t, or I'll call it VL of t. Just V out. How about V out of t? We want that. Well, in your past life, the way you did these things was you didn't write differential equations. After you got done with Dave Irwin's class, you said, well, this is just J omega L. We're going to be in the frequency domain, right? This is R. And then this has to be either a cosine or a sine, constant frequency, or a DC source. But you never had this, right? So now what we have to do is write the differential equation first, right? And then solve the differential equation for that variable by doing a Laplace transform. Y'all with me? Matter of fact, just to be consistent with what I think was in the problem, I think this was y of t. I'm not actually sure. All right, so now what we do is take a look at these things and talk about what the voltage is around here. Because we're going to, y'all agree it's a series circuit, right? It's a complete loop. So the sum of the voltages around any closed loop is zero, right? For this one, I know y of t, this voltage, would be equal to L times di dt. Right, I know that for a fact, correct, class? And I'm going to do this two ways. The first way is I'm going to take a look and actually solve for the current, then the voltage by taking a derivative, all right? And the second way is to show you the trick with Laplace transform. Are there any initial conditions for the current in the inductor? Is it nothing? If there's not an initial condition stated, it's not assumed. Sometimes they'll put an initial current here at t equals 0, follow me? But if there's none, then you don't assume it. So now for this, I know the voltage here across the resistor is simply I of t times R, right? The voltage across the inductor is L di dt, and this is the voltage here. So when I start at this point and I go around clockwise, I get this. I get an increase of 20 e to the minus 3t u of t, then I get, this would be minus I of t times r, right? And minus L dy dt, correct? Isn't that right? But what I'm gonna do is this. I'm gonna take those to the other side. So this is going to be equal to, then it becomes plus I of t times r and plus L dy dt. How many see this, what I've done? I've written a circuits equation, nothing funny, nothing fancy, just like you've been doing all through your circuits courses. And by the way, you did that in physics too. Now I take the Laplace transform of both sides. Got me? Take the Laplace transform of this becomes 20 over s plus 3. Do you all agree with that?
Mm-hmm.
All right, so that's straightforward. Now on the other side, what happens? Now I'm going to have r times I of s, right? And then I'm going to have plus L, whatever L is, times the derivative of I with respect to t, the transform of that. Well, that's s times, this is really going to be s times I of s minus I of 0 minus, right? It's really the value in the time domain. That's the initial condition. Are you all grasping what I'm saying? Now the initial condition doesn't exist, so we make our lives easy, just get rid of that. And get rid of that bracket. Now I have this, correct? Now, what I want to do is get the transform. Now, what are the value for R for this one, by the way?
10 mils.
It's 10, and L is what? 15
50 millihenries.
50 millihenries, all right. So this is going to be, that's 5 times 10 to the minus 2, right? Correct, class? Now I factor out the I of s. Follow me? I want to just get everything next to I of s. That's what I'm solving for. So when I factor out the I of s, I get I of s here times the quantity 10 plus 5 times 10 to the minus 2 s is equal to 20 over s plus 3. You with me on this? Now here's the first thing I'm going to call your attention to. Anytime you have Laplace transforms, the pairings, for exponentials, you have e to the minus at u of t, that pairs as 1 over s plus a. Agreed? Now, what that means is this: the coefficient of s has to be 1. All right, if you look there, our coefficient is 5 times 10 to the minus 2. Did you follow me? So now, what I'm going to do is take 5 times 10 to the minus 2 out in front of this. And that means I have to divide this by 5 times 10 to the minus 2. Do you all agree with me there? Now what I really have is what? 10 over 10 to the minus 2, or 10 times 100 or 1,000 divided by 5, which is 200, isn't it, class? So that's 200 is really what's going to happen, I believe, unless I mistakenly. So there's 200 plus s times 5 times 10 to the minus 2. Agreed? Now, how many are with me on this one? All right. Now, what am I going to do? I'm going to solve for I of s by itself. This is one way to do this problem. There's another, but I want to show you this way from the fundamental differential equation that you're used to seeing. You're used to taking sums of voltages around and closing them equal to 0. You know the voltage across a resistor is I times R. You know the voltage across an inductor is L dy dt, correct, class? So those are things that are common knowledge that you know, and now you're going to apply Laplace transforms to get the solution. So I solve for I of s, and I'll put it up here. And that means my I of s is equal to, we're going to cover several things with this one, 20 over s plus 3, right? And it's divided by 200 plus s, and it's divided by 5 times 10 to the minus 2. And 1 over that is what? 100 by 5 is that 20, class? Right? So when I take 1 over this number, I should get 20. So that's 20 squared, which is interesting. Do you agree with me, everyone? How many work this one has got basically? Did you solve for I, first of all, or not? You don't have to. You can actually solve, you could say, if this is the voltage here, right? You could say that this voltage, well, to be frank about it, it would actually take a little doing, but you could work your way into an equation for just Y, but I'm gonna do it this way for a reason. All right, now when I have this, I don't know the inverse transform of that one. Follow me? But here's where we use something called partial fraction expansion. And it leads, this is a perfect way to lead right into the next logical thing, which is, if you've got Laplace transforms, how do you get back to the time domain? And that's it. We do not do the inverse Laplace transform integration that you'll see in the book. We use partial fractions, and then we recognize what the transform pairs are. That's the way we do it. So I'm going to do it over here. I'm going to leave that pairing up here. Now, for partial fractions, how many remember partial fraction expansion? You had to use this in your mathematics courses a fair amount. You're going to use them in engineering a whole lot. Like from here on out, you'll be doing it tons of times. So what if we have something where if I have k over, they're called simple poles, if the power of s is 1, and it's not like s squared or s cubed or something like this. If I have s plus a times s plus b, and I want to get back to the time domain with this. So what I do is partial fractions. I recognize there are two poles. The poles mean the value of s that would send it to infinity. When I see s is equal to minus a, that goes to 0, and 1 over 0 is infinity. That would be a pole. Agree, everyone? The second pole would be s is minus b. There are two simple poles, and I'll get to complex poles. If this is s squared plus a squared, that's a complex pole. Right? That's a higher order pole. We'll get to that one later. So now we put one constant, call it c1 over s plus a, plus c2 over s plus b. Now y'all know if we can get c1 and c2, this is the pairing we've got then, right? It's easy to get back to the time domain. Does everybody see this, class? It's easy. So now how do you find c1? I'm going to go through this once in the full method of doing it. Then I'll show you what's called the cover-up. If I multiply everything by s plus a, that goes away. You don't have to do this, just watch. S plus a. And then s plus a goes away here, right? Now, if I let s go to minus a, what happens? That goes away. You all see that? So now that goes away. And I have the value of c1 equal to simply whatever that constant was over minus a plus b. That's called, we're finding it's called a residue. We're finding the partial fraction coefficient. Got me on that one? Now the way normally professors teach this, I think, anymore I'm not sure. Normally if you have a constant, and it can be as many poles as you want, s plus a, s plus b, s plus c, and we could go on and on until we're just sick of it. You put c1 here over s plus a, c2 here over s plus b, pardon me, c3 here over s plus c, and hear me now. This is something I believe everybody in the room was exposed to, whether you remembered it or not. And by the way, Laplace transforms and differential equations are sort of your life in engineering. I mean, it doesn't matter if you're mechanical and aerospace. You just kind of live in this domain to solve differential equations. So I multiply I'm just going to work on this function. Call this my x of s. All right. I'm going to go ahead and just cover up the s plus a if I want c1. Now I know automatically what I'm really doing is multiplying through by s plus a. And then I evaluate what's left when s goes to minus a, because that's where that pole exists, right? So now I can say that c1 would be equal to k over, and it would be minus a plus b and minus a plus c. And that would be c1. How many see this right here? Right? You see it? I mean, I'm asking you, do you see it? Because I want to make sure everybody sees this. Do you remember, how many remember the cover on that? I call it the cover because you're covering things. You remember this from your, how many had differential equations here? Let's try that. How many had Laplace transforms here? All right, then every one of you should have seen this, unless your professor was willfully ignorant. Because this is like fundamental to solving the inverse Laplace transform. Now, applying it to that, if you take a look at this, what happens? Well, how many poles do I have just by looking at that? Two, right? If you'd like, I'll make that 400 on top. I have 2. So I know it's K1 over S plus 3 plus K2 over S plus 200. Right? How do I find out what K1 is? I cover up the S plus 3, right? And I evaluate the remainder at S equals when it's minus 3 there, right, class? Now you all see that's 400 over 200 minus 3, or 197, right? So this becomes 400 over 197. I don't know the value for that off the top of my head, but that's what you do. Do you all agree with me? What about the next one for K2? What do I do? I cover up the S plus 200, right? And I evaluate the remainder at S equals 7. Minus 200. And what would that be? Well, that would be minus 200 plus 3, right? Or minus 197. And it would be 400 over minus 197. I have a comment here. Anybody notice something strange about those two coefficients? One's the negative of the other one. And anytime you have a constant over two simple poles, the first constant will be the second constant will be the negative of the first. That's always the way it is. How many remember that from the day you had different kids? Nobody? Well, it's one of these things that kind of sticks with you when you get about the 30th problem you're doing like this, you kind of notice that. All right, now, regardless of what these values are, I mean, this is about 2 right here. This is about minus 2, about, right? All right, when you go back to the time domain, what happens when I do the inverse transform? Well, this is going to become what? That coefficient, 400 over 197 times what? Now it's going to be e to the minus 3t, right? Times u of t. What about this one? That's minus 400 over 197. Then it's going to be times e to the minus 200t, right, times u of t. And that's I of t. That's in the time domain, isn't it? How do you get the answer that we're looking for? Y is L times di dt, so what do? We multiply that by the value of L, which is 50 millihenries, right? Or 1 over 200, right? And which is nice, because it's going to scale that thing down. We multiply it by that and take a derivative. What happens when you take a derivative of these? I'm going to caution you about one thing. The u of t is the problem child here. Because when you take a derivative of this times this, you take the derivative of the first times the second, plus the first times the derivative of the second. So you're going to get delta functions. And those, by the way, do not occur. It's a fictitious thing in this case. And I'm going to get to something to show you how to do these problems. But anyway, if you take the derivative of this with respect to time multiplied by L, then you will get y of t. I'm pressed for time here, and I want to get this one point. I want to show you how to actually do these problems using Laplace, the normal method with Laplace transform. And for the way to do them, if you have no initial conditions, I want you to just write that down on a piece of paper, no initial conditions. Then what you do is this. You know that anytime, if I'm looking for like the voltage on a resistor, oh heck, I'm going to run out of time. Here's what happens. If you're going to take a look at this in the S domain, think of the J omega domain when you were dealing with Irwin's class, all right? When you had circuits, what happened? If you went into the frequency domain, the only thing that happened is R remained R, right? Remember that in the phasor domain? Well, what happens when you have a derivative? What happens to an inductor here? It would be J omega L, right? Now instead of j omega L, the impedance of this is just going to be SL. S is like j omega. This is only for no initial conditions. So now this becomes 20 over S plus 3. Do you all see this? Right? Don't worry about the R value, right, and the L. Now, what do I do in circuits if I want the voltage across two series elements? I get the voltage across both elements. This is in the S domain, just like you did in the j omega domain, right? That's going to be 20 over S plus 3. Then you're going to multiply it by the impedance. This is like the impedance in the frequency domain. Just think of it like j omega L. By that impedance, which is SL, and divide it by the series impedance, which would be R plus SL. And that would be your Y of S. And then, to get the value of the functional form, you do a partial fraction expansion of those two terms, solve for the constants, and then realize it's just two exponentials. Do you all see this, class? How many see this? Show of hands. Who asked that question? Does that answer your question?
I got the first.
What?
I got the first way you did it.
All right, do you understand this way? You're just taking the j omega that you lived with, right? And replace it with S, if there's no initial conditions. And then do the Laplace transform of the source voltage. Oh, okay. All right, now you got a quiz coming today. That's the reason I'm a bit in a hurry. So take everything off your desk, please. And make sure